Thank you. So, as I had announced on Monday, I mean, we've been maybe a little behind schedule, but still today is the day to go into the quantum non-commutative realm. And I should start by saying that what I was talking about the past 3 days, I think we've reached a point where it's kind of quite elegant and somehow conclusive, and I'm quite confident in that material that it's kind of nice and useful. But this is not very much the case for what I'm going to talk about today, and this is a lot more tentative, and there's things that I'm really not satisfied with, and I will get to, and maybe some of you will have some ideas on how to improve on that. Okay, so time permitting, I want to talk about two possible approaches to kind of categorical quantum probability. The first one is going to be what we've called evolutive Markov categories. And the second one is, if there's enough time, I'll get to that. What's what we call a semi-Cartesian probability, which is a much weaker setting to start with. Okay, but yeah, I think I'll spend most of the time on the evolutive Markov categories, because this is a bit more developed and also has more structure to talk about. Okay, so yeah, let me state the definition. And so the idea is to, well, do something like for Markov categories, but now we want to do this for operator algebras. So basically, think of this. So I'm not sort of trying to develop formalized sort of operational things in physics, but think of this more as taking an operator algebras textbook and taking the things in there and then abstracting away from those and trying to generalize those to a categorical setting in the same way as we've done for Markov categories and probability. So it's more like a categorically generalized operator algebras theory. Okay. So an evolutive Markov category, evolutive here, well, yeah, should remind you of the involutions in that we have in operator algebras. And yeah, I actually don't want to write down the full definition because it's a lot of it is parallel to classical Markov categories. And so let me just be a little informal now and say here it's like a Markov category, and then I'll just write down what's different here. So except in that we have a kind of involution as additional structure. So there are involution maps. We go from every Hom set to itself. You know, this is maybe a little surprising at first. Maybe you would expect that it reverses source and target, but we'll see why that's not the case here, or why we don't want it, why we want actually the source and target to be preserved under the involution. So, and for related reasons, we don't denote it by a star, so we do it for the involution of C-star algebras, but we denote it by a bar. Yeah, and well, this should satisfy some conditions. Basically, it should just be functorial and an involution, and functorial in a monoidal, even in a monoidal way. So let me write these things down. So when f and g are composable, then when we compose them, their involution should just be the v bar f bar, and the involution of an identity should be itself. And also note here we cannot reverse, since that's for the same reason as why this is not reversing source and target. We can have to like.
So basically you're introducing the complex side, the complex number only in this sense. Yeah,
That's a good way to put it, yeah. And then we'll see in the example how it corresponds to that. Okay, and concerning the tensor, the parallel composition, G tensor F bar, now F and G are arbitrary. Also, just the obvious thing should be, should factor like this, and finally should be involutive, right? So F bar itself. So yeah, you can think of it as a kind of complex conjugation. And of course, if we have the morphism, the morphisms can be their own conjugate, then these are the self-adjoint ones. And we call these self-adjoint. Okay, so these are the conditions that concern the involution only. But of course, this should also be compatible with the other structure, Markov. So the copy morphisms in particular. And this is the final condition. I'm not sure if there's maybe a better way to denote this, but then we just put the bar on top here to say that this is the involution applied to a copy morphism. And this now reflects the thing that taking the involution in C-star algebra reverses the order of multiplication. And so here this is not literally a copy itself. We don't want it to be a copy itself, but we want it to be the copy with the order of inputs. Well, yeah. Okay, so this is the definition in a little informal way. And now let's maybe look at the example, or let's take actual operator algebras and see how these form an evolutive Markov category.
This is an additional axiom.
Yes, right, yeah.
If you don't have the conjugation, then it becomes the usual factor with monoids commuted. The evolution unit.
This replaces the condition that the copy should be commutative. Obviously, we will not have that anymore. Okay, so what we really would like to have, and I'm leaving a little space here since I'm going to have to fix this because it doesn't quite work. So we would like to have, again, C-star algebras, basically as our objects, and introduce then an evolutive Markov category, which has C-star algebras as objects. And well, we will want the copy morphism to be the formal opposite or formal dual of the multiplication, right? Oh, by the way, I'm gonna now consider morphisms as now today gonna be consistently working in the Heisenberg picture. I think it's the most convenient. So throughout, I'll just write morphisms the opposite way in the past few days that actually use the, so we should read the diagrams now consistently from top to bottom. And so the copy is multiplication, or we want it to be multiplication in this example. And since this multiplication is not positive, let alone completely positive for a non-commutative algebra, we cannot just take the positive linear maps or something, or well, it's not even self-adjoint, of course. So that means we have to go to a larger class of maps. And in this sense, I think it's how represents more like the operator algebra textbook than physically operational things, the morphisms. Right, in the operator algebra textbook, well, you consider non-self-adjoint maps all the time, like the multiplication. Okay, so this is what we would want. That means for the morphisms, we need to just consider a larger class. And what we take is maybe there's something better here, a better choice. I'm not sure. But what we've been working with so far is just take all unilinear maps.
No continuity whatsoever.
Oh, that's okay. Yes, I'll go to that right now. So unilinear maps. And multiplication is copy. Unilinear maps as morphisms. Okay, so now concerning the continuity, well, since we want the multiplication in here, and for the tensor product, let's say we take to make our lives as easy as possible, concerning the multiplication, we should take then the maximal tensor product. But even then, the multiplication is not continuous, right? It's not bounded. And this is the first point that I'm not satisfied with in the framework. So we use, let's say, the maximal tensor product of these two algebras as the tensor product as the monodal structure. Then so now this doesn't work if we want bounded unilinear maps, or even, well, I still need to fix the thing, need to fix things anyways. But so now, either way, the problem is that a multiplication is not bounded. I think actually any infinite dimensional non-commutative C algebra. No, is that true? No, probably not quite. But as soon as sort of the non-commutative part is somehow infinite dimensional, I think you run into trouble. So, but certainly, let's say for B of H, infinite dimensional H, clearly the multiplication is not continuous. Or well, doesn't even exist as a map like this because of the failure of boundedness. So this does not make sense.
In a sense, you could just use star algebras.
Yeah, that's the fix that I'm gonna be implementing now. I'm not really satisfied with it. I mean, I feel like there should be a better solution to this, and I thought about things like maybe taking another tensor product, and so there is a kind of tensor product that does make the multiplication bounded. It's a Haurup tensor product, but then that has other issues. Like, I think the tensor product of two C-star algebras is not a C-star algebra anymore.
In the Agrap tensor product?
Okay. Right.
So it's just a Banach-based tensor product?
It's a tensor product of operator systems or something like that.
So like modules, it's associated to fiber objects, so like modules object.
You mean something like Hilbert modules, C-star modules, or no?
Yeah, no, sorry.
No, it's more a tensor product of operator systems, something like that. Okay, yeah, so as Florio indicated, so then the fix that we've implemented, that we've been working with so far, is just to actually use well, for one thing, use the algebraic tensor product, basically work with star algebras instead, or what we've been considering so far is pre-C-star algebras.
The Descartes instructor is a unit, right?
What?
If you remember,
Sorry?
the Descartes instructor of the category is a unit of the algebra?
Yes, that's right, yeah. Yeah, so then we use pre-C-star algebras as objects which are the same as C-star algebras, just without the completeness requirement. And then we can consider the algebraic tensor product as monoidal structure. And then it's still frustrating because, well, the unital linear maps as morphism, we still need to allow all of the multiplication is still not bounded. So that means we still allow all unital linear maps, regardless of continuity.
So, is there any reason why you look in the other way around instead? Because otherwise you could look in this direction, and you could consider off algebra, so co-algebras for the paper.
Yeah, sure. I mean, you can, but then let's say if you want to formalize categorically all the structure of hot algebra, then you have both, right? Then you have the multiplication and the co-multiplication.
Yep.
So then we're in a setting where you have both a copy and a co-copy that suitably interact and so on. I mean, I think I like kind of the resolving graphical calculus of hot algebras, and I think it's useful, but it would just be something a little different.
How about completely positive?
Yes, I will get to complete positivity later. I mean, of course, you want to somehow restrict to that in a sense. Okay. Oh, I forgot to write down the involution, of course. But maybe that was already, you may already have guessed it, that when we have for f from A to B, from three C-star algebras, oh, I should also add the 3 here. Well, it's f bar is just defined as f applied to A star. So here's the star in A, and then the star of the result in B. That's kind of the obvious thing on then the linear maps and in the algebras, how to define an involution. And so now the self-adjoint maps are precisely those that commute with the involution, right? So the ones that are positive maps and categorical do that, of course. Okay, and maybe it's worth noting a conceptually big difference relative to what Urs has presented or is presenting these days. that in ortho setting, the category, the morphisms of quantum types are basically linear operators, right? Or operators themselves. Whereas here, we're this category, evaluative Markov categories, sort of axiomatize maps between the algebra, so more like at the CP level, at the channel level. So in that sense, I would say it's not surprising somehow that maybe the formalism is very different. Okay, so now let me say a little bit about what one can do with this and how one can express some kind of basic operator algebra concepts just now in this language. So maybe the most obvious thing is a concept of classical object. So we can now express commutativity. Of course, it's just saying that the copy is commutative. So an object A is classical if the copy is commutative or equivalently if it's self-adjoint. So far, I guess this is pretty obvious and maybe not so interesting. What's a little more interesting maybe is that we can, if you know the universal property of the maximal tensor product, it says that basically whenever you have two morphisms into the same C-star algebra and their images commute, then that extends uniquely to a map on the maximal tensor product. The maybe surprising thing is that we can express this and prove this property for the monodal structure on any evaluative Markov category. So purely from this definition, we can state and prove this.
The commutativity now is this property.
No,
I mean,
we need to talk about commutativity of images.
Okay, so you are going to.
That's what I'm going to write down now. So the setting is that we have two morphisms that land in the same object, right? A1 to B, F from A1 to B, and G from A2 to B. And now I want to express this idea that the images commute. And this is, I guess, it also has to do with compatibility, in a more kind of physical operational sense, compatibility of measurements, and in some way. So we call two morphisms like this compatible if the following equation holds. That if we basically use multiplication in B, so it's kind of a more complicated version of this commutativity classicality notion. Okay, so yeah, let me just write this down, what this compatibility amounts to in our running example. Well, then to see what it means, we basically just need to plug in, for each wire on top, plug in an element, right? And then show that, or see what the equation says when we do that. So of course, that's basically amounts to using the fact that the elementary tensors span the algebraic tensor product, right? That's why it's enough to just plug in individual elements, as opposed to general elements of the tensor product. Okay, so then, oh, and maybe I should write down also the typing here. So it'd be an F, we have A1 on the top right and A2 on the top left. Okay, so then we plug in an element little a1 here and little a2 on the left, then and we multiply them by taking f of a2 first, a1 first. Right, and on the right hand side, well, we just have the same thing, but written the other way around. Okay, so yeah, in our example, this says precisely that the image is commute. In the usual sense that's relevant for the universal property of the maximal tensor product. Yeah, okay, maybe as another part of the definition, we also sometimes have considered a morphism to be compatible with itself. It is also that's also a non-trivial condition. I mean, if you take G to be equal to F, there's no reason for why a particular this would hold. I mean, the identity is not compatible with itself unless the object is classical, right? In that case, it's precisely the classicality. So F is autocompatible if it's compatible with itself as finally. As it's
Sorry. Yes. So you could have a monic from a classical object inside a non-classical object. Could you reconstruct some sub-classical system in this way?
Potentially, I guess it depends on what you want to. You mean the image itself?
Yeah.
Have a sort of image factorization. I can imagine, yeah, that there's maybe some sort of.
So the idea of a measuring apparatus could be implemented in this way.
Well, for measurement, we can just say it's an autocompatible morphism, or it's or you can just say it's a morphism.
From a classical.
From or to, and I need to make sure not to get confused. From a classical object, right? We can just say measurement is a morphism from a classical object. Period.
But must be injected somewhere or not.
Why would it? I mean, maybe it's a degenerate sort of measurement that always produces the same outcome. Yeah, okay, so this is autocompatibility, and then there's one more definition that is kind of maybe potentially interesting and easy to state using compatibility. I'm not sure if our terminology really accurately reflects the physics here, but we've been saying that F is non-invasive if it's compatible with the identity.
That means that basically elements are sent into the center of.
Exactly, yeah. So if we take our G to be the identity here, well, then this can be an arbitrary element of B, So the condition is that it commutes with everything in B, meaning it F lands in the center. Maps to the center. So that would be
You get some relation between Borel-Stokes and this pre-sister algebra. Can you see it as a subcategory? I don't know. Is there a functor between the two? Can you recover whatever you did in this framework of pre-sister algebras?
I mean, there is a functor, but I think it's not a particularly nice one. And what we can do is to assign to a standard Borel space, or even any measurable space X. It's L infinity of X, by which I mean all bounded measurable functions without any sort of, well, we have no reference measures, there is no quotienting or measure equality here. This is a C-star algebra. And well, also now on Markov kernels, you have a Markov kernel X to Y, you can view it in the Heisenberg picture as basically going the other way, which is essentially sort of something like conditional expectation again, right? And then we do get a functor like this, but it doesn't preserve the monoidal structure. I mean, surely you won't get the algebraic tensor product, so it's a kind of related to my question of what is a quantum measurable space, or non-commutative measurable space, if you want. If we had a good definition of that, and could replace the pre-sister algebras by that, then I would expect to get a nice functor that preserves the monoidal structure and is fully faithful, so that basically Borel-Stokes would be precisely the subcategory of classical element objects.
Would you say that this is a requirement for a good quantum theory?
I think it's maybe not a strict requirement, but it's definitely, if you have a category that satisfies this, then I would take this as a strong hint that we have a good candidate definition. And if we have a definition that doesn't satisfy that, then you better have very good other arguments for why it's useful. And yeah, so we've also worked on just to maybe shouldn't have maybe erased this L infinity. Been investigating properties of C-star algebras that maybe would somehow be in between C-star algebras and W-star algebras, and that kind of characterize algebras like this. And I could talk about that as well, but I guess that would be another kind of slightly different topic and a different talk. And again, I'm not really satisfied with the answers anyways, so. Okay, so now I had mentioned that we can prove the universal property. Now I just want to write down the precise statement of this. So yeah, we are in an involutive Markov category now. And then the statement without any additional assumptions needed. And then the statement is that we have a canonical bijection. So in the sense of an adjunction, really, or universal property again. between deterministic morphisms A1 tensor A2 to B. So now these are arbitrary objects, and deterministic, well defined in the same way as we've seen in the classical Markov categories, meaning these are the star homomorphisms. I've already talked about that, right? And so on the one hand, and on the other hand, we would have in the classical case, we would simply have pairs of morphisms, the classical Markov category, from, so now in the Heisenberg picture in this direction. And then, so this is the correct statement in the classical case, and this is exactly when I had said that deterministic morphisms form a Cartesian monoidal subcategory. That's the statement here, right? Basically, universal property of, with this direction of arrows, A1 tensor A2 is just a co-product of A1 and A2. That's what this says. Okay, but now in our current setting, where we don't have the classicality, just need to modify this to assume or include compatibility condition here. So compatible pairs in that sense. So yeah, this is provable directly from the definitions now, and obviously we haven't really set up much of a theory so far, so it's pretty straightforward. Okay, so yeah, this is kind of the basic setting so far, and I think it's somewhat nice, except that this is really kind of frustrating, and maybe this is, I'm not sure if this is somehow just not the right example to look at, or is this an indication that the whole framework is maybe not so good after all? I don't know. I'm happy to hear your opinions. Okay, so but now as Hayato had already asked, or what about complete positivity? Here we just have too many morphisms. And well, so maybe the boring answer is that we just sort of put that on top as an additional structure, as a additional designated subcategory. And so that's in the following definition. I may be using a little simplified terminology and a simplified definition than we have in the paper. So we call these pictures, and I want to present a definition that is a little stronger, and so let me just call this a little easier to state, so let me call this good picture. So in an involutive Markov category, sorry, before I get to this, I forgot to mention something more basic about the definition of involutive Markov category. So the definition that I have presented, so this is one from our paper, but there was another one a little early, from a few years earlier, by Arthur Parsingham, of what he calls a quantum Markov category. And we've shown that it's essentially the same concept in the sense that you can intertranslate. The difference is that in his definition, he has the involution of an algebra itself as a morphism. So in his category, he has, at the concrete level, he has not just linear maps, he also has anti-linear maps, including the involution. And so his categories is basically that the home sets all have kind of two parts, a linear part and an anti-linear part. And so that's why we have the involution kind of as additional structure on top of the category. and then only linear maps as morphisms. That's why we haven't called our categories quantum Markov categories, because that concept had already existed. Okay, so yeah, now moving on with this. A good picture is a well, subcategory and a closed-ordered tensor and basically symmetric monoidal subcategory. So let me just write it like this: symmetric monoidal SMC. We've seen this acronym a bunch of times now. Symmetric monoidal category, symmetric monoidal category, and let me denote it by D and C. And think of this semantically now really as designating morphisms as completely positive. This keeps track of which morphisms are completely positive, and then correspondingly in our example, we'll take this to be the completely positive maps. Okay, and well, in general, our abstract axioms are, it contains all the delete maps. So the inclusion of the unit in an algebra is completely positive. And then one further condition related to the compatibility. Okay, let me just write if F and G are compatible, and then it's understood that they have the same codomain. And they are indeed. Then also the corresponding pairing like that over there is indeed. Maybe element is a little too abusive notation, so is indeed. Okay, and this is also a property of completely positive maps. Basically, that suppose at least you take with respect to the maximal tensor product. If you have two completely positive maps that have commuting ranges, then again, the resulting induced map is completely positive if you use the maximal with respect to the maximal tensor product. Basically, universal property also holds if you replace deterministic. Sorry, this is missing deterministic. If you take CPU morphisms instead of star homomorph.
So you're asking it to contain all the latents, in particular it contains every object, or are we asking only?
Oh, yes, that's right. Yeah. Mm-hmm. So sometimes, yeah, maybe I should have made that more explicit. People call this sometimes subcategory contains all objects of Y subcategory. Oh, actually, so yeah, concerning the tensor product, we can have two choices here, or we can take any, in principle, any functorial tensor product of pre-C star algebras. Particularly, we can take the minimal one or the maximal one. And I should have been more precise here, because just the algebraic tensor product, when I write that, we don't have a norm on the tensor product algebra. but I had said that the objects are pre-C-star algebras which do come with a norm. So actually I should correct this and say that it's we have two versions of the category. We can take the minimal tensor product to define the norm, or we can take the maximal one. As far as just the involutive Markov category is concerned, it really doesn't matter. The morphisms are the same anyway.
Because your morphisms are not necessarily continuous.
Yeah.
So they don't feel
Yes.
this. Okay.
Yes, exactly. But now when we look at a picture and we define a complete positive, look at what morphisms are completely positive, now it makes a difference. Okay, so yeah, that means concerning the examples of pictures, we have these two possibilities. Let's say, yeah, let's start with the maximal tensor product. So now we call it CPU max in pre-C star. Let me put a subscript max here to indicate also there the maximal tensor product. This is a good picture. If we take the minimal tensor product instead, then the situation is a little different. And well, then we no longer have this property in general. But we have only a weaker version of this, and so now this is what we call a picture in general. I'm really not much of a fan of the definition, because it seems a little clunky, but basically we weaken this condition to just assuming an addition F is autocompatible, so it lands in the center and then it still works. So this is merely a picture. And yeah, for the full, and I don't want to give the full details here, and maybe it's better just focus on this case. Okay.
So you don't ask for the having all copies. That is the
Exactly. Yeah, we cannot because multiplication is not completely positive.
it's not a Markov category inside.
Exactly, it's not. Yeah. On the classical objects, I think it is. Should maybe carefully check that. But then, well, then the identity is autocompatible, and so then we get the case of this condition, then we do get a copy with F and G both being identity. Okay, now yeah, there was some interest yesterday in, or was it already on Tuesday, the distribution objects. And so now I can get to the quantum, or to the non-commutative version of these. And this is actually in the concrete case where C-star algebra is a kind of an old story that I'm just kind of warming up in a bit of a different language. So yeah, or we're just kind of generalizing the definition. But the fact that these exist is kind of something that goes back to Kirchberg, I think, and another kind of one of these operator algebra people. So yeah, when we look at a good picture and an object in there, now I'm just writing down the definition of distribution object again, and it's just it has the exact same form as in the classical case. Except that now I'm writing the direction of arrows the other way around. but it's in principle it's just the same thing. So let me write it, spell it out again. So a distribution object is P, A, and D with a natural bijection so general morphisms from A into B into any B now should correspond to deterministic morphisms. From PA into any B. And well, into the same B. So yeah, let's think about this and for the example. So for C-star algebras or pre-C-star algebras even, then that means that we consider CPU maps, let's say out of a given C-star algebra A, and we want another C-star algebra which sort of classifies these CPU maps. Right? In the sense that the CPU maps out of A should correspond to star homomorphisms out of PA. Has anyone seen these? Have you seen these before? Okay, yeah, well, so these do indeed exist. And so one way to construct them, if you've heard of operator systems before, then this is basically the definition here also. One way to construct them is to forget the multiplication on A and just consider A as an operator system, which just keeps track of what complete positivity is. And then you take kind of the enveloping C-star algebra of that. It's technically called universal C-star algebra, and these have been constructed, are known to exist.
And when A is a billion, like is some C of X or L infinity, what happens?
Yeah, so let's look at some examples. Let's maybe start with the okay. So in general, in CPU, here it doesn't matter. This is not about a tensor, right? So we can choose either of them. These exist and are essentially. So let me qualify this a little bit, because technically we have just the pre-C-star algebras and not C-star algebras, so this is a little technically different than what I'm going to write down, and are the universal C-star algebras. So essentially the universal C-star algebras. These exist and are of the underlying operator systems. Okay, so getting back to Floyd's question, let's make this concrete and look at some kind of very simple examples. So what about maybe the most trivial example? Let's just start with C itself. Well, a CPU map into any B, there is only one, right? Must take the unit to the unit. So meaning it's automatically a star homomorphism. And that means that, or in other words, now our A is initial, so then PA is also the initial object. So here it's just C again. Up to isomorphism or whatever. Okay. Now, let's look at the next non-trivial case. C2. Now, what do you think our distribution object is going to be? Or how do we describe CPU maps out of C2 into any other B?
Sorry, what were the deterministic maps here?
The star homomorphisms.
Show maps for the positive. The graph decomposition, no? So how we associate to this homomorphism, we have to associate to any of these.
I'm not sure how to phrase it in terms of the cross decomposition right now. But I think it's actually easier in that we don't even need that.
C2 is not
yeah. So
Basically, I want to turn a positive map from C2 to B into a star homomorphism.
Yeah, yes. And so for that, we first maybe need to think about what are the positive maps out of C2 into B.
Functions of the identity, basically. So you decompose the identity into...
Exactly, just into two positive operators. So in other words, I mean, or we can put it like this, I mean, in C2, we kind of have our two standard basis vectors that are projections, and their sum is the identity. So they're complementary projections, and well, then we only need to look at one of them. Meaning, in other words, this is sort of universal C-star algebra generated by a projection.
But why is it a projection? Because positive maps, they don't necessarily lead to projections.
Right. No, I'm just talking about C2 itself for now, not the image in B.
Okay.
So when we apply the map, that projection, well, then that maps to a positive operator in B, and such that its complement and 1 minus it is still positive. So and otherwise it's completely arbitrary. Right, so this means that the completely positive maps basically correspond to the unit interval of B, the sense of the self-adjoint operators between 0 and 1. Okay, now how do we obtain this unit interval as a star homomorphism? Well, if you think in terms of functional calculus, it's precisely, I mean, in other words, it's the operators in B that have spectrum in the self-adjoint elements whose spectrum is in a unit interval. And so these, by functional calculus, you can then extend to star homomorphisms from functions on a unit interval, right? So this is how we arrive at continuous functions on the unit interval.
But this is also for C3, for C4, Cn, right?
Yeah, so now let's consider that the next, and this C3 I think is especially interesting. So for C3, we now have, instead of just a single projection, we can look at, let's say, the first standard basis vector 1, 0, 0, and then let's take 1, 1, 0. So now we have sort of an ordered, a total ordering of these standard basis vectors, and we can map them arbitrarily to positive operators in B as long as this ordering is preserved. Basically, so this means that morphisms, CPU maps from C3 into any B are now pairs of elements of the unit interval in B that are ordered with respect to another. And now, but these do not need to commute. Right, so this means that if we now translate this into what this universal algebra is, basically it's the algebra freely generated by two elements between 0 and 1, and that are ordered, but they do not commute, so this thing is going to be non-commutative. So, well, I'm not sure if there's a more explicit description of it than other than writing it down kind of in terms of generators and relations as I just sketched, but this kind of shows that it has to be it's going to be non-commutative.
But this is already a very huge departure from the classical.
Yeah.
I mean, if you get these, then there is no hope that the classical Markov picture is embedded in any meaningful way in this category. Because in that case, the distribution object is basically P of X.
Well, the embedding would not preserve these distribution objects, but yeah, I think that's fine. I mean, it could still be a nice way. Maybe not as nice, maybe not sort of 100% nice, but still maybe nice enough to do things with it. Okay, so these are kind of the genuinely non-commutative distribution objects. There's another concept of distribution object, and this is kind of a small variation on this, and then we sort of we necessarily obtain commutative objects, classical objects. And in that case, what Florian was saying would also not apply. And as I had, I think, already mentioned on Tuesday, for commutative C-star algebras, we had, as a Markov category, we had obtained the state spaces. And now the exact same thing happens here. We can characterize state spaces in terms of the universal property. But now a state space is of non-commutative of any objects. And so that's what this definition is going to capture. And so again, for any A and D, now we call it a state space object. Space is then SA. So this is required now by definition, must be classical. SA. Together with a natural bijection. That is literally the exact same thing. But just for classical B, only needs to be defined for classical. I mean, we can expect it only to be defined for classical B. Yeah, and so we've shown that this exists as well, and that it corresponds essentially to functions. So if you really take, continuous, if you require us to be complete C-star algebra, then it would be continuous functions in a state space, and in our pre-C-star setting, it just comes out to be the polynomial functions in a state space. By polynomial, I mean the sort of, you take the evaluation maps, which are linear functions in the state space, and then you can look at kind of the algebra generated by those, and you multiply them, those are, and add them, those are polynomial functions. Okay, so I could also state quantum definity theorem, which is kind of also another kind of interpretation of what a state space object does. It's a little less satisfying than our classical version because we haven't proven it in terms of the categorical formalism. We've just stated it while we've proven the classical version. Or I could directly move on to the other approach of semi-Cartesian probability, and then we still have a little time for that. Any preferences?
I would like to see the other approach also before.
Okay.
I agree with you.
Okay. Yeah. Great. Good.
I'm not-
Then let's move on to that. Okay, so this is semi-Cartesian probability. And I guess I should already point out that this is so far very much underdeveloped. So I can just, basically what I can do is to kind of sketch a few ideas for the moment, or well, a little bit more than ideas, but so far there isn't really much. Okay, and so here, the starting point is to say that, well, since the copy is, or the multiplication in the algebras is not completely positive, let's just forget about it. And let's just try to see what we can do without. What can we do if we just stick with, in terms of the examples, stick with CPU maps only? And so that makes this into an alternative approach without copy. And it kind of may look a little impoverished, but my hypothesis kind of is that if we're sufficiently clever, you can still actually do a whole lot with this. And I want to sketch then some possibilities. So alternative approach without copy. And if you, I don't know how much interaction or contact you have with more like these quantum foundations community, people who think about really how one can, for example, reconstruct quantum mechanics from more operational physical axioms. Since like the multiplication of operators, nobody knows what it physically means anyway. So I want to have more meaningful operational axioms. And then consider these, what they call general probabilistic theories, where you just assume that you have some kind of abstract state space given by a convex set of a suitable kind, but does not need to be the state space of a C-star algebra or something. And then they consider basically positive maps between these and so on. And so this is semi-Cartesian probability is kind of the categorical version of that in a sense. So this applies, meaning it applies to these so-called general probabilistic theories. And I think could be an interesting setting for that.
This
So-
means in these general probabilistic theories, they do not have the copy.
Right.
And so the
Mhm.
inference, also from the probabilistic, the inference should appear in some other way in this sense. So you cannot have the definity, or you have a simple, a different, you can do inference only in some way. So
There actually still is a definite theorem. But I don't know how to formulate it, let's say in a categorical language. That's actually a good question. Yeah, would be worth thinking about, I suppose. So then this as I said, then it looks kind of superficially too impoverished, but I have the feeling that if you're just clever enough, one can still formulate a lot of things, and probably the definite theorem is one of those things in this language. And I'll demonstrate that with one or two examples where I know how to do it. Okay, so the definition is, yeah, an SMC, a symmetrical nodal category, is semi-Cartesian. If the monodal unit, so the thing that when we tensor with it trivializes the tensor, so like the complex numbers as a C-star algebra. If this monodal unit is terminal, so basically the terminal object, so what this amounts to is we still have the deletion morphisms, and they behave in the same way as in the Markov category, but we no longer have to copy. And so the idea being that now this is the more kind of physically operational thing. You can, and the idea being that you can just always ignore any system, and that amounts to deleting marginalization. Okay, so yeah, the sort of examples to maybe keep in mind would be, and here we also have no longer this problem of just with the multiplication, continuity of the multiplication. Now here we can really just restrict to C-star algebras and take completely positive maps or and whatever tensor product we like, the minimal or the maximal one, or I'm not actually sure if there are other functorial ones. I've been searching a little bit and haven't found any results along the lines of C-star tensor product would be both functorial and associative. If anyone knows, I'd be interested in hearing about that. Okay, so yeah. So in the last 15 minutes, I want to just write down basically some definitions of how one can express some things that are some interesting properties in this purely semi-Cartesian language. And to do that, I need a concept of a dilation. So yeah, a dilation of, oh, I'm not sure if I should use which direction of arrows. Yeah, maybe let's stick with this, the operator algebra direction of arrows. So then we have A to B. So this is any dilation is any Q. A tensor E, and so think of E as standing for environment, environment system, such that, and maybe you already guessed it, that the P should arise from Q by just discarding the environment, or in operator algebra terms, by plugging into the unit element. It's been a while actually since I thought more about kind of the non-commutative setting. So right now, I couldn't actually quite reconstruct how this relates to sign spring dilations and things like that. Maybe someone can say. And it's not exactly the same, right? But I think one can also formulate things like sign spring dilations in this as these kinds of things. Or I mean purifications and this kind of thing in a more quantum information language. Purifications of states are like this. Okay, and so our observation has been that working with dilations, it seems to be one way to avoid using the copy or to get around the problem that we don't have any copy available. And so to give one example of how this works, let me define now the semi-Cartesian analog of almost sure equality. We have seen almost sure equality for Markov categories, and the definition crucially involves the copy. But now, using dilations, I can state a version that does not use the copy, but is equivalent in under suitable assumptions. So F and G, A to B are B dilationally equal so P is something like a reference measure, reference state with respect to which we want to define something like almost sure equality. So for P, that means P should now need to be careful with the direction of arrows. So this should go from B into something else. Let me call it F, maybe since C, usually write C for the category, right? If for every dilation Q of P, we have an equation that kind of looks like almost sure equality for Markov categories. And I'm also going to draw that again, but for now, let me just write that down. So yeah, if you can just replace F by G, and it gives you the same thing, sort of in the context of Q. Okay, and so what we've shown is that this is equivalent when we are in a suitable Markov category. So now classical. To well, to almost sure equality. And so let me just also draw this again. So it's equivalent to this. in I don't think in every Markov category, but in every Markov category that satisfies one of our information flow axioms. We have presented the positivity axiom and what we need to assume here, and which holds in many or maybe most of our examples is what we call a causality axiom. So this holds in every the equivalence unit of dilational equality, almost sure equality holds in every causal Markov category.
You mean every causal Markov category that is also semi-Cartesian?
Oh,
Or by using the given
So,
deletium maps instead?
a Markov category is always semi-Cartesian.
Okay.
Basically, because we have the deletion maps, and semi-Cartesian means that we have deletion maps.
But do we have that they are unique?
Yes, exactly, because there's exactly one morphism to this unit object from any other one, and that's the deletion. Okay, so we haven't actually worked out what this amounts to in the C star in a non-commutative operator algebra setting, but I'm pretty sure it's something like when you quotient by a corresponding null state. So if you take, for example, P to be a state, then this must be something like F and G coincide modulo, no, yeah, something involving the corresponding null space.
Let's find ideas.
Hmm?
Let's find ideas.
Gelfand? What?
And the states on the algebra on which the state is zero.
Yeah, exactly. Okay. It's called Gelfand ideal.
Yeah, it's associated to a construction.
I see. Okay, I didn't know that. Yeah. Thanks.
You have to square.
Yeah. Okay, so this is kind of one example of how one can get rid of the copy if one really wants to, and with sufficient cleverness come up with alternative definitions that achieve similar things. Yeah, and maybe one more example, and then I'm done. There's for Markov categories, I have presented the positivity axiom as a kind of information flow axiom. And what could information flow axioms look like for semi-Cartesian probability? Something that expresses something like a positivity or things along those lines. And I want to present one of these axioms. And for that, I should recall the definition of no signaling. And I suppose many of you know this, again, from a more like maybe quantum information context. So this is something that we can now formulate in every symmetric monodal category. F tensor G, let's say, is no signaling. If there is. So basically what I want to say before I complete the sentence, what I want to say is that if you discard the B system, then this channel does not actually depend on the G input. And so this means that there should exist, if there is some little g from A to F, such that when I actually do discard this, in physical terms, this is an output, then this should be equal to just discarding the G input and using the little g. It's called no signaling because now the idea being that wait, which way did this go? I think that the G input does not transmit any information to A. Right? Because if you only look at the A, then it only depends on F. Yeah. Okay, now this is a definition that comes from the thesis of Nicholas Huden Larsen, who was a student in Copenhagen, and who had kind of developed a good deal of quantum, a certain amount of quantum probability in the semi-Cartesian language. And this is maybe actually the one reference where the semi-Cartesian approach has been developed the most so far. And yeah, I can give you the reference if anyone wants to look into this. So this is an information flow axiom, and he calls it the Di Vincenzo property, named after a quantum information theorist. Maybe some of you know him. It was Lorenzo Di Vincenzo. No, sorry, too much. Yeah, I forgot it. Not sure. So a semi-Cartesian category satisfies the Di Vincenzo property if every no signaling channel like this morphism, like above F, can be decomposed into two parts. So it can be written as that the F, and this is something I think is very intuitive, and that's why I like this axiom. If you can write the F in a way that first creates basically this first output on the left just as a function of the left input. So I maybe want a little more space. So first does this, but also creates some sort of message. And if you want, you can now think of this in terms of Alice and Bob. Alice kind of operates on the left side, Bob on the right side. And so the point is that Bob cannot signal to Alice. That's what we're assuming. But on the other hand, maybe Alice can signal to Bob. And that's exactly what this decomposition is going to do. So basically, Alice does something on her side and maybe prepares the message for Bob. And that's what this intermediate wire amounts to. And then Bob does something. This is basically you want morphisms that you can plug into these boxes such that F factorizes into this form. And that's the Di Vincenzo property. And so Nicholas proved that this holds in CPU. Well, okay, he had done it for a finite dimensional setting. But I suppose this proof probably generalizes. So here's showing that quantum channels satisfy this. Okay, so yeah, then I'm at the end, and I hope it's been at least a little bit interesting, and happy to discuss more.